The history of the atomic theory started in ancient Greece in 460 BC. At this time, people were not able to use the technological devices that modern scientists have access to. And so instead they theorized and tried to use what they know to find an accurate explanation of the composition of the universe. Democritus was born in Abdera, Greece in 460 BC and was the son of an extremely wealthy nobleman. He had a terrifying hunger for knowledge and traveled the world. When he returned to Greece, he occupied himself with the study of natural philosophy. He contributed much to scientific knowledge of the ancient world, but the most notable of his contribution is the explanation of the atomic theory. According to Democritus' atomic theory, the universe and all matter obey the following principles. Everything is composed of atoms, which are physically but not geometrically divisible. Between atoms lie empty space. Atoms have always been and always will be in motion. There is an infinite number of atoms and different kinds of atoms, which differ in size and shape. And finally, atoms are indestructible. He wasn't the first to research the composition of the universe. His mentors Lupercus and Epicurus were believed to have proposed the earliest view of the shape and conductivity of atoms. However, Democritus was credited for his pictures and explanations for the concepts as well as his influence on later philosophers. Now let's discuss how a philosopher tried to become a scientist. Believe it or not, but his views were rich with flaws and errors. You might have heard of someone named Aristotle. His theory of the 5 elements was widely accepted and believed for almost 2,000 years after his death. Aristotle was born in Stagira, Greece in 384 BC and lived and worked there for almost all his life. Just like his mentor Plato, Aristotle grew up to be known as a great philosopher and even taught Alexander the Great. However, when the atomic theory was proposed, Aristotle didn't believe in it, and instead he taught that all matter is made out of 5 elements: fire, water, air, earth, and ether. It is important to remember that this theory is incorrect and it is largely based on observations. John Dalton was born on September 6, 1766 in Eaglesfield, England to a Quaker's family. Both he and his brother were born with color blindness, and because he was from a poor family, he started teaching at a Quaker school when he was 12 in order to support his family. When he was 18, he was made the principal of the school and also taught at New College. His fascination with gases led him to experiment and conclude that all matter, whether it is a gas, solid, or a liquid, is made out of tiny particles. He referred to these particles as atoms, a term borrowed from Democritus. Along with rediscovering the atomic theory, he wrote articles and books on the subject of atomic weight and became the first scientist who explained the behavior of atoms in terms of their weight. There are 4 parts to his atomic theory. The first part of his theory states that all matter are indivisible and make up all matter. The second part of his theory states that all atoms of a given element are identical in mass and properties. The third part states that compounds are a combination of 2 or more atoms. And finally, the final part states that a chemical reaction is the rearrangement of atoms. Dalton's atomic theory is the first complete attempt to explain all matter in terms of atoms. After his second stroke, Dalton died on the evening of July 26, 1844. His research outlived him, changed the course of science for chemistry, and allowed for a gradual progression into modern science. Joseph John Thomson, who was always called JJ, was born in Cheetham Hills, England in 1856. His father wanted him to become an engineer and sent him to Owens College when an engineering apprenticeship cannot be found. After he graduated from Trinity College at Cambridge, he started to work in the Cavendish Laboratory. In 1894, Thomson started to study cathode rays, which were beams of light that followed an electrical discharge in a high vacuum tube. It was a popular topic that was studied by many physicists because the nature of cathode rays was not understood. Cathode ray tubes are steel glass tubes in which most of the air has been sucked out. A high voltage is applied to one end of the tube across 2 electrodes, which causes the negatively charged cathode to move to the positively charged anode. These rays could be detected by painting phosphorus on the far end of the tube beyond the anode. The phosphorus material will emit a spark or light when hit by the cathode rays. In his experiment, Thomson placed 2 oppositely charged electric plates around the cathode ray tube and found that the cathode ray was repelled away from the negatively charged plate, but attracted towards the positively charged plate. This showed that cathode rays are made up of negatively charged particles. When Thomson passed cathode rays through the vacuum, he was able to calculate the angles at which they were reflected off and calculate the ratio of the electrical charges to the mass of the particles. Using this knowledge, he determined that all matter is composed of particles that are smaller than an atom, which we now know as electrons. Beginning of 1906, Thomson began to study positively charged ions or positive rays. This led to a second discovery in 1912 when he channeled a stream of ionized neon through a magnetic and electric field and used deflection techniques to measure the charge to mass ratio. By doing this, he found that the neon was composed of 2 different kinds of atoms and proved the existence of isotopes. Thomson won the 1906 Nobel Prize in Physics, among many accolades. He died on August 30th, 1940. When Thomson died, he was buried near two other influential scientists, Charles Darwin and Isaac Newton. Ernest Rutherford was born on August 30th, 1871 in New Zealand. Similarly to Thomson, his family had financial difficulties and struggled to raise their family of 11 children. However, at a young age, Rutherford began experimenting and sought after academics. He landed his first scholarship to Nelson Collegiate School, a private secondary school, and later another scholarship to Canterbury College. Later, he was invited by J.J. Thomson to work together on the study of X-rays, which was found months before Rutherford's arrival at the Cavendish laboratory. The two scientists studied the effects of X-rays on the conductivity of gases, which resulted in a paper about dividing atoms and molecules into ions. While J.J. Thomson went on to find electrons, Rutherford continued his study of ion-producing radiation. In an experiment, Rutherford found that when he placed a uranium block next to a thin foil, one type of radiation was blocked, but the other type was able to pass through the foil. He named these two types of radiation alpha and beta. The alpha particles were found to be the same as the nucleus of a helium atom, whereas the beta particles were found to be the electrons. Following these discoveries, in 1907, Rutherford conducted his famous gold foil experiment along with his assistants Geiger and Marsden. In this experiment, a thin beam of alpha particles was fired at a thin sheet of gold. This sheet of gold was surrounded by detector screens that would flash when hit with an alpha particle. And even though most of the alpha particles passed through the gold foil, about 1 in 20,000 particles were deflected more than 90 degrees from the path. This proved to Rutherford that the positively charged nucleus occupied a tiny volume of the atom, and nearly the total mass of the atom was concentrated in the nucleus. Also, this showed that most of the atom is made out of empty space. With this discovery, it paved the way for the nuclear model, and won him the 1908 Nobel Prize for Chemistry. Rutherford died on October 19, 1937, leaving a legacy that will lead to the discovery of nuclear fission. James Chadwick was born on October 20, 1891, in England to a poor family. Chadwick began studying at Victoria University in Manchester in 1908, and in 1910 he was working in Rutherford's laboratory on research projects. During the time in the university, Chadwick struggled with financial difficulties until he received his master's in physics at age 21. After, he went to work in Geiger's laboratory in Berlin, Germany. But World War I broke out and he was detained until the war was over. After World War I, Chadwick returned to England and continued his nuclear research in the Cavendish laboratory. At this time, many scientists, including Chadwick and Rutherford, believed that there was a possibility that a particle that had no charge could be located in the nucleus. Through the 1920s, Chadwick experimented in his free time in order to prove the existence of the neutron. And in the year 1932, Chadwick learned of the work of two other scientists in Paris, Frederick and Irene Joliot-Curie, who believed that they managed to eject protons from a sample of wax by bombarding it with gamma rays. Chadwick didn't believe that gamma rays had enough energy to eject the protons of wax, but the notion that wax was hit with sufficient energy to eject the protons was convincing. Thus, Chadwick concluded that the wax was hit by neutrons as polonium decayed. With this knowledge, he experimented with polonium and wax and measured the protons' behavior. Protons behaved in the same exact manner as if they were hit by an electrically neutral particle with the same mass as a proton. With this discovery, Chadwick won the Nobel Prize in Physics in 1935 for his discovery of the neutron. The discovery of the neutron changed the course of chemistry and physics. It meant that neutrons can collide with the nucleus, so when it increased the atom's mass, and by the process of natural beta decay, which was the emission of an electron from the atom's nucleus, would then convert the neutron into a proton. Also, with this discovery, it showed that neutrons could be used to split heavy atoms or atomic fission, releasing massive amounts of energy. This can be seen in nuclear reactors or in nuclear weapons. Chadwick became one of 3 men who were able to access all information about the Manhattan Project during World War II. He was present at the Trinity test on July 16, 1945, which was the first atomic bomb that was ever detonated. 19 years later, James Chadwick died at the age of 82 on July 24, 1974. Niels Bohr was born on October 7, 1885 in Copenhagen, Denmark, and received a doctorate degree from Copenhagen University in 1911. That same year, Bohr was able to travel to Cambridge. Following close behind the works of Rutherford, Bohr felt compelled to elaborate on the idea that lighter negatively charged electrons were able to circle around the heavy positively charged nucleus without falling towards the nucleus. In 3 articles published in a philosophical magazine in 1913, Bohr explained that electrons could only occupy particular orbits determined by the quantum of action. Also, Bohr reasoned that electromagnetic radiation from an atom occurs only when an electron jumps to a lower energy orbit. And with the Bohr model, physicists are able to accurately predict the spectral line series emitted by hydrogen. Bohr took his findings and sought to improve them in order to understand the periodic table of elements in the 1920s. For his work, he was awarded the Nobel Prize in 1922. When Adolf Hitler came to power in Germany, Bohr used his connections to get physicists out of Germany and ultimately obtaining permanent homes in the US. When fission was discovered, Bohr was aware of the theoretical possibilities of making an atom bomb. Thus, he talked that there are practical obstacles that cannot be overcome in the path of creating the atom bomb. And even when Heisenberg, a German scientist, visited him, Bohr remained unmoved. However, after escaping the Nazis to London, he was informed of the Allies' atomic bomb project and willingly joined it after concerns about a corresponding project in Germany. After the end of World War II, Bohr was allowed to return to Denmark, where he was welcomed as a hero and spent the rest of his days calling for responsible and peaceful applications of atomic theory. He died on November 18, 1962, in his home city, Copenhagen. Later, his son will share the 1975 Nobel Prize in Physics with two other scientists for the research on motion in atomic nuclei. Erwin Schrödinger was born on August 12, 1887 in Vienna. Schrödinger attended the University of Vienna, where he graduated a PhD in physics in 1910. When World War I began, he was drafted into the Austro-Hungarian army and served as an artillery officer. After the war, Schrödinger worked as a professor at the University of Zurich, where he learned of the work of a physicist, Louis de Broglie, who proposed that electrons act like waves. The next year, in 1925, Schrödinger wrote a paper that highlighted something that would be known as the Schrödinger wave equation. With the Bohr model and the thesis from de Broglie, Schrödinger explained the movement of electrons in terms of wave mechanics. In 1927, he left Zurich for a new position at the University of Berlin, where he met Albert Einstein. He held this position until Hitler's rise to power, which caused him to leave Germany and began teaching at Oxford University in England. While at Oxford, he received the 1933 Nobel Prize in Physics, sharing the award with another quantum theorist, Paul A.M. Dirac. In 1944, Schrödinger published the influential book, What is Life?, which attempted to connect quantum physics and genetics. In later years, he published two other books, both of which focus on philosophy. Schrödinger returned to Vienna in 1956 after teaching in different countries, including Austria and Ireland. He died on January 4, 1961. Werner Heisenberg was born on December 5, 1901 in Germany and studied at the University of Munich until he received his PhD in 1923. From the year 1924 to 1925, he worked with Niels Bohr at Copenhagen. During this time in the 1920s, Heisenberg formulated his uncertainty principle and published it in a 1927 paper. Later on, he would refine his thoughts in subsequent lectures and papers. The uncertainty principle states that we cannot measure the position and the momentum of a particle with absolute precision. The more we learn about one value, the less we know about the other. With this principle, physicists are able to explain things that classical physics cannot explain, such as why negatively charged electrons do not fall towards the positively charged nucleus. If the electron gets too close to the nucleus, then its position can be calculated with fairly accurate precision. However, this means that its momentum or its velocity of the electron is not known, meaning that the electron could be traveling at such speeds as to fly out of the atom. Therefore, the electrons maintain a stable distance away from the nucleus. Of course, another way to explain this is with kinetic and potential energy, but we will save it for another video. Along with other research projects, Heisenberg also worked on developing a model of proton and neutron interactions, also known as strong force. This research and model earned him the Nobel Prize in 1932. In the same year, the National Socialist German Workers' Party, or the Nazi Party, also saw their rise to power. This sparked the beginning of a series of events inspired by anti-Semitism, including the removal of many prominent Jewish scientists from their post who left to America or England. Heisenberg stayed in Germany and was the leading scientist in designing the atomic bomb in Germany. Regardless of what role he played, the research team that Heisenberg was in charge of was unable to create a reactor or a bomb. At the end of World War II, Heisenberg was captured by American soldiers and was detained along with other German scientists in England. A year later, he was released and continued his search for a comprehensive quantum field theory. After the war, Heisenberg did much to reorganize scientific research, and in the later years of the 20th century, he published many books, including an autobiography. He retired in 1970 and died on February 1st, 1976 in Munich. Max Planck was born on April 23, 1856 in Germany to a jurist and professor of law at the University of Kiel. Planck, after graduating from secondary school, chose physics over music. Nevertheless, music was a staple part of Planck's life and he found peace through the keyboard. Planck entered the University of Munich in 1874 and received his doctorate degree in 1879. From there, Planck taught at the University of Kiel and then later Berlin. Planck's most important work stemmed from the subject of the laws of thermodynamics, and by showing that the problems of radiation processes were considered as electromagnetic in nature, he was led to the problem of the distribution of energy in the spectrum of full radiation. Planck was able to derive the relationship between the energy and the frequency of radiation, which was based on the idea that energy emitted by a resonator could only take a specific value or quanta, and published his findings in a 1900 paper. This is now called Planck's constant. Planck suffered many tragedies in his later years, which resulted from the emergence of the Nazi Party and the devastation of World War II. He died on October 4, 1947 in Göttingen.